In this video, we are going to implement forced versus random failure of nodes, which is also called attack survivability. We are going to take a network and we will be removing nodes from this network, and we will observe the effect of removal of nodes from the network. We will be using two strategies to remove the nodes. In the first strategy, we will remove the nodes randomly, and in the second strategy, we will remove the nodes which are highly connected. We will observe that when we remove the nodes which are highly connected, it requires very less iterations for the graph to become disconnected. This sort of information can be used by some agent. For example, if he has the information of who is more connected and who is not, if in case he wants to damage the network, for example, by spreading some sort of virus, he will not be attacking the random nodes. Rather, he will attack the nodes that are more connected, so that the network becomes infected to a greater extent. So that is one thing we will observe and implement, and we'll also see one more thing in the context of the kinds of graphs. For example, the first thing that we checked on real world networks. Real world networks sort of follow preferential attachment, where there is existence of hubs in the network which are responsible for connection of most part of the network. So when you remove them, the graph becomes disconnected. We are going to observe the same thing, that is the removal of nodes, on random networks as well, and we will observe that it doesn't make much difference on a random network when we remove the nodes randomly as compared to when we remove the nodes selectively. That is, we remove the nodes which are having high degree. That is because there are no hubs in random networks which are responsible for the connection of most part of the network. So the number of iterations that it will require in the first case, that is random removal, and the second case, that is selective removal, in the case of random networks, will not make much difference. We are going to implement that, and we'll observe the number of iterations that are required. Let's get started with the implementation. Let me import the packages first. We might also need random package. Okay, let's define our main. I already have downloaded a real world network, that is email network, and that is in edge list format. We will be making use of that. This network is basically undirected, so there is a link from node A to node B if they exchanged any email with each other. So that sort of network is what we will be using. Let me read that network. nx.read edge list email.txt. Okay, I've kept this in the same folder where I have kept this file. And then let me print some details about this network. So I'll write nx.info so that I get the basic statistics about the graph. Let me call this function. Let's now check whether the graph has been read or not. It has been converted into a graph object or not. So this is the basic statistics about the graph. It has more than 1000 nodes and more than 5000 edges, and the average degree is there. Okay, so let's get back here. So we are going to remove the nodes from this network in two ways. Let me print the first way, random removal. Okay. Okay. We are going to randomly remove the nodes. Let me create a copy of the given graph, because we are going to remove nodes in two ways. So we'll work on both the copies. So this is the first copy, G1, from which we will remove the nodes randomly. First, let's check whether the graph is connected or not. Is G1 connected? Okay, I'll write nx dot is connected G1. Okay, we have to keep a track of how many nodes had to be removed to make the graph disconnected, okay, when we randomly remove. So let's create a variable nodes removed when we randomly removed, initialized to 0. Now while the network becomes disconnected, we have to keep removing the nodes. So we'll write nx dot is connected g1. We have to keep removing, so we should better create a function for removing a node. I'll create that function in a while. I'll write g1 is equal to remove a random node. So this function I will just create. I'm going to pass the graph here, okay, and as we keep removing, we'll increment the counter for nodes remove random plus is equal to 1. Okay, and in every iteration we'll keep checking whether the graph is connected or not. We'll actually print that. And let me just copy paste this. I'm sorry. Okay, so at every iteration we're going to check whether the graph is disconnected or not, and in the end, when we are done, we'll come out of this loop when the graph becomes disconnected, and at that point of time we'll print the number of nodes that needed to be removed to make the graph disconnected when randomly chosen. Okay, we'll print nodes removed random. Okay, we'll ask the user to press and enter here as well as here. Okay, we are going to remove in the second strategy, we are going to remove the node selectively based on the degree. So let me just copy paste this entire thing and I'll just make changes into that. So in the second strategy, we are removing selectively, selective removal. We'll create another copy, G2 of the graph. We'll see whether G2 is connected or not. So I'm just making changes there. Nodes removed when selective removal was there. Let me write selective only, selective, and again G2, and here also G2, and nodes removed selective is G2 connected. We actually should have written G only here. Anyway, nodes removed when when selectively chosen. Nodes removed selective, right? Yeah, I think there's no mistake here. Okay, the only thing left is now to create this function, that is these two functions. We have, wait a minute, we have to remove the node selectively. Okay, so remove high degree node maybe. Okay, so we are yet to create these two functions. The first function is remove a random node, and the second function is remove a high degree node. Let's create these functions. Okay, this function we have to create. So out of all the nodes, we have to choose one node randomly and we have to remove that. Let me get a list of all the nodes. Nodes is equal to g dot nodes. I have to randomly remove a node out of this, so I'll use random dot choice out of nodes, and we have to remove it. So I'll write g dot remove node. Which node to be removed? R has to be removed, and at this point we have removed a node from the graph and we will return it. Okay, let's make it generalized, just keep G here. So we passed the G and we returned the G. So whichever graph was input, one node was removed and it was returned. So that function is being used here. Everything seems fine, the syntax and return type, everything is fine. Next thing is to create this function, remove a high degree node. Let's create this function now. Okay, what do we have to do here? We have to see the degrees of the nodes, and we have to sort them accordingly, and the node which has highest degree will be removed. How do we do this? Firstly, let's get a dictionary having the degrees of all the nodes. So g dot degree. Okay. Now out of this dictionary, we have to get a sorted list of the key value pairs, right? So what we can do is, these are basically not nodes, these are edges, because when we sort a dictionary, we get a list of tuples where every tuple is actually key and value, where key is node and the value is degree. So yeah, it makes sense to call it nodes. So what we can do is, we can use the sorted function, and we'll pass degree, degrees. Degree might be a keyword because degree is the name of the function, so let's call it degrees. Degrees dot items key is equal to lambda, the same old method that we use to get a sorted dictionary. And then x, we want to sort based on the value, and we want to sort in descending order. Reverse is equal to true. This should work. I'm sorry. So what is nodes? Nodes basically is a list of tuples where the tuple, to place center here, where the tuple is having two things, node and the, let's check it, node and the degree, right? And it is sorted. So the first node will be having the highest degree, and that is what we should remove. So we'll write g dot remove node. Which node we have to remove? Out of the nodes list, we have to take the first entry, that will be a tuple, and out of that tuple we have to take the first value, that is going to be the node that has to be removed, right? So now let's return g. Okay, this should work if there's no mistake. So we are calling that function here. G2 is equal to remove a high degree node, and we are incrementing the counter, and we are printing. That's all. It should work. Let's check. So this is the basic statistics as we saw earlier too. I'm pressing enter. Okay, so in this case we are randomly removing, and we had to remove only one node to make the graph disconnected. Now I'm pressing enter, and we are now selectively removing, and again we needed only one node to make the graph disconnected. So by chance in this case, as you see, whatever node we removed randomly, that was by chance a high degree node. That's how the graph becomes disconnected. Let me run this function again, and let me see. Oh, again it is taking one. That's surprising. And again, let me run this again. So in this case, you see random removal took 16 iterations, and the selective removal took only one. Let me run this again. Again, in random removal it took 13, and in the selective one it took 1. I'm just going to run it last time. So again, in random it took 17, and in selective it took 1. You can just keep checking that. Okay, so that is one thing. In case of real world networks, this sort of thing happens. Now we are going to check the same thing on a random network. Okay, so let me write here that all this was for a real world network, or a network which basically follows power law, distribution, and preferential attachment. Real world networks, right? This doesn't look good. Let me write this. No, this doesn't look good. Let me write this. So okay, this was for real world networks. This looks very bad. Anyway, let's go ahead. So next we are going to do the same things for a random network. Now how can we create a random network? Okay, Okay. In the previous videos, we created an Edwards-Rennie network. We can use that code to create a network, and we can also use a function from network X where we have a function where we pass the values of n and p and we get a random network. So in order to tell you the function, I'll use that function only over here. Let me call the graph H. I wrote nx dot Edwards-Rennie network. So this is the name, I'm sorry, graph. So this is the name of the function, and let me pass some n, the total number of nodes, and the value of p, the probability. This should give us a random network. Let me print the basic information of H. After that, we want to remove the nodes as the same way we did earlier. Let me copy paste the entire code here and we'll make changes into that up to this, right? So I'm just pasting the entire thing here. Random network starting here, okay. Raw input and then random removal. The graph name is H. What did I do? Okay. H, we are making copy of H, and then we are checking whether H1 is connected or not, and nodes removed is fine. Then NX is connected H. If I could have actually used a replace function here, it's okay. So everything else remains the same. I'm just changing the graph here. Okay. I actually should have used the replace method, but I think we are done. We're almost done now. Okay, last one. Alright, so I think we are good to go. We have just taken a random network now, and we are applying random removal as well as selective removal in this case, and we are printing the number of iterations that are required in both the cases. Okay. Since we have already observed the behavior on a real world network, let me comment that part so that we are able to concentrate on only real world networks. So I'm commenting this part up to which point? Yeah, this point. Okay. So let us check our code. So this is for random network. We have 1000 nodes and these many edges. I'm pressing enter. Random removal is taking place. So you see this is taking a lot of time. It's taking a good number of time. It's actually going on and on. As you can see, it's going on and on. Still going on. Okay. So the number of nodes we had to remove from a random network when we randomly chose them was 985. It's a whopping 985. I'm pressing enter here. Now we are selectively removing. That is, we are choosing the nodes with high degree and then we are removing them. It's again going on and on. Surprisingly, it's going on and on. Let's still going on and on. 928, as you can see. So in the case of random network, when we randomly removed the nodes, it took us some 938 nodes to make the graph disconnected, and in case when we remove the nodes based on their degrees, that is, we remove the high degree nodes in every iteration, it again took us 928 nodes to make the graph disconnected. Now that is happening because there are no hubs in random networks which are connecting a lot of nodes. So all the nodes are sort of equally likely, because equally likely in the sense of the number of nodes that they are connected to. So there is no preference because the edges were added randomly, and there is no preference towards addition of nodes to some particular nodes in this. So that is the sort of difference that we observe in case of real world networks as well as random networks, because real world networks are not random, and they show they actually exhibit some sort of preference towards the nodes.